Good day, students. Welcome to math.serve.com. In this clip, we're going to be going over how to simplify radicals. To get us started, we're going to take a look at the main property of radicals that is going to guide our problem solving process today. Okay? Alright, so this is the formula. It's the inverse property of radicals. So the formula is as follows. It's the inverse property. Think about inverse as opposite. Now, if you have a radical with an index of n, or you can call this the nth root of some radicand, which is x to the nth power, this becomes x. Okay? So what this property is telling us is that if the index of the radical is equal to the power of the exponent, an inverse operation occurs in such a way that these two basically cancel themselves out, and then you're just left with x. Okay, so that's the inverse property of radicals that we're going to be using today. Just to illustrate, let me show you some examples. So let's say we have to find the square root. No, let's not do that. We want to find the square root of x squared, for example. Now, one thing you want to note is that when you're writing down the square roots, the index is 2. The index of your radical is 2, but it's invisible. Okay? So imagine that there's an invisible 2 here. So this is the same thing as 2 root x squared. So since the index of the radical and the power of the radicand are the same, guess what? These two cancel themselves out, and you're left with x. Okay? Let's take a look at the cube scenario. Let's say you want to find the cube root of 5 to the third power. If the index is 3 or greater, you have to specify it. If the index is 2, then you don't have to put any number there. Okay, so this 3 is appropriate. So what is this going to be? Now, since the index of the radical is equal to the power of the radicand, what happens here is that they cancel each other out. Cancel, and you are left with 5. Okay, so just remember that this number, this little number in front of the radical symbol is the index, and it's invisible for when n is 2. And this is basically, we already know what this is. This is the power of the radicand. Okay, so if they are both identical, we have an inverse relationship happening. And when you compose inverse functions, you know that they normally cancel each other out. Alright, so keep this formula in mind as we take a look at some examples. Alright, the instructions for the examples that we're going to be doing are as follows. Simplify the following radical expressions. The following radical expressions. So let's say for number 1, we are asked to find or simplify the square root of 32. Okay, so just deal with a constant this time. So there are different methods that can be used to simplify radicals. We're going to be using the prime factor decomposition method here. Okay, it's not necessarily the fastest, but it shows you exactly what's going on. So what we're going to do is we're going to decompose 32 into a product of primes, and then use the prime factor decomposition of 32 to simplify root 32. Okay, so how do we do that? To get us started, let's write a list of some of our prime numbers here so that we can refer to that easily. The smallest prime is 2. We have 2. The next one is 3, 5, 7. 9 is not a prime because 3 goes into 9. 11, 13. So prime numbers are numbers that are divisible by just themselves and 1 alone. Okay? Alright, so these are some of your primes. Now, when you're doing prime factor decomposition, you just take a look at your list of primes and ask yourself, what is the smallest prime that goes into the number that we have here, and then you can decompose it in ascending order. Okay, so since 32 is even, we know that 2 goes into every even number, so 2 goes into 32 16 times, and then we can decompose 16 further since it's composite. 2 goes into 16 8 times. That can be broken further. 2 goes into 8 4 times, and then 2 goes into 4 2 times. Now, if you wanted to use the square root method, you could have just taken the square root of 16 here, and you have 4 root 2 as your answer. But we're using a different method that reveals all the factors. All right. Okay, so how do we proceed here? Now, what we're looking for are squares in the prime factor decomposition. Why are we looking for squares? It is because the index of a square root, if it is not specified, is 2. So this 2 tells us that any product of two identical numbers can come out using the inverse property of radicals. Okay? So let's look for our pair of factors that are identical. So we have 2 and 2 here. Now these two 2's can come out of the radical. They will come out as a 2. And then we have another pair of 2's right here. Just to help you see what's going on, if you take a look at this 2 and this 2, that is 2 square. Okay, and then this 2 and this 2 is another 2 square. Now, how about this 2 right here? It's by itself. It's not double, okay? It's not 2 times 2. It's not a square. Sorry. So since it doesn't have a partner factor identical to it to break out of the radical with, this 2 stays behind. Okay? So let me illustrate what we're about to do. So we have 2 square. What is the square root of 2 square? So we're going to take the square root of the 2 square, and then we'll take the square root of 2 square, and then we'll take the square root of 2. So the square root of 2 square, notice, remember there's an invisible 2 here, and that 2 cancel out. So these 2 are gone, so you're left with 2. So if you have a factor that repeats in the decomposition of a radical, that factor can come out as what? As 1. So these 2 times, these two 2's can just come out as a 2. Okay, because it's 2 square. And then the next 2 times 2 is also a square. When you take the square root of a square, they cancel each other out. Bam. So this one comes out as a 2. And then this 2 right here, you see the problem? The power of this 2 is just 1. It's not identical to the index, which is 2. So that means that it cannot break out of the radical symbol. Okay, remains as a radicand. So this root 2 stays behind. Now, what do you do with the two numbers that are out? The two numbers that broke out because they have partners, you basically multiply them. So 2 times 2 is 4. So 4 root 2. That's what your answer is going to be. Okay? So let's go ahead and write it down. The square root of 32 is equal to the product of these two numbers, 2 times 2 root the number that couldn't break out because it's alone. And then you have 2 times 2 is 4, and 4 root 2 is the simplified form of the square root of 32. Alright, let's go ahead and take a look at another example. Now for question number 2, what if we're asked to simplify the square root of a variable? Alright, so this one will be slightly different, but we'll apply the same procedure. You shouldn't have any problems with it. So for problem 2, let's say we want to simplify the square root of 180 n to the 4th power. Alright, let's do this one. So what we're going to do is we're going to decompose 180 n to the 4th all the way down to its to a product of primes. Okay? And then since this is the index is 2, we're going to be looking for factors that occur twice. Okay? So we're looking for pairs or squares so that they can come out of the radical as a root. Okay, so let's see, 180 is even. We have our prime list here, so we can start from 2. 180 is even, so 2 goes into 180 how many times? 90 into the 4. This is even also. 2 goes into 90 into the 4 times 45 times. So since 45 ends with a 5, we can pull out a 5. 5 goes into 45 into the 4th 9 times. And then what goes into 9? 3 goes into 9 3 times. And then we can decompose this n to the 4th. Okay, n to the 4th is just simply n times n times n, and multiplied by itself 4 times. Okay, so remember, since we have an index of 2, the square root, we're looking for pairs of products to break out of the radical symbol. So let's see. What are the pairs we have here? 2 and 2, that's a nice pair. That's a square. 2 times 2 is 4. So the square root of 2 times 2 is just going to be what? 2. So that breaks out. 5 is by itself, so it stays behind. It doesn't have a partner to break out with. Oh, nice. Look at this. We have 2 pairs. We have a pair here. 3 and a 3, that's 3 square. What is the square root of 3 squared? The square root of 3 squared using the inverse property is 3. Okay? So remember, every factor that repeats, if you root it, you just end up with one of them. That's what the square root does. And then if you look at the variables, we're still looking for pairs. Okay? An n and an n, that's a pair. What is the square root of n times n? The square root of n times n is just n. So that breaks out as n. And then we have another pair here. The square root of n times n is n. Alright? So the terms that broke out of the radical symbol, since they were squares, are 2, 3, n, and n. 5 was alone. Okay, it didn't have a partner to break out with, so it will stay behind as a radicand. So what is our answer going to be? In expanded form, the square root of 180 n to the 4th is 2 times 3 times n times n, the numbers that were squares, 2 square, 3 square, n square, and n square. And then we have the root 5. 5 was not a square, so it doesn't get to break out of the radical symbol. Let's simplify this. 2 times 3 is 6. N times n is n square. Root 5. Ladies and gentlemen, 6n squared root 5 is the simplified form of the square root of 180 n to the 4th power. Okay, so that's the answer to question number 2. Let's take a look at one more example. All right, for question 3, let's consider the square root of 216 x raised to the 3rd power. Okay? All right, let's do this one. We're going to follow exactly the same procedure that we followed for problems number 1 and 2. We're using the prime factor decomposition method here. Okay? So we have the square root of 216 x to the 3rd. Now, what are we looking for in the decomposition of 216 and x to the 3rd? We're looking for factors that occur twice, right? So we're looking for squares. Why are we looking for squares or factors that appear twice? It is because the index, as indicated before, of the square root is 2. So that tells us that we need terms with a power of 2 so that we can apply the inverse property of radicals in their simplification. Okay? So let's break this down. Using our prime factors, this is even, so 2 goes into 216, 108 x to the 3rd times. 2 goes into 108x to the third. 54x to the third times. It's still even, so 2 goes again into 54. 27x to the third times. 3 goes into 27. How many times? 9x to the third times. 3 goes into 9. X to the third how many times? 3x to the third times. So since this is a prime, this remaining number here is prime, I can go ahead and decompose x to the third into x times x times x. Okay, so what we're now going to look for is factors that repeat twice. Okay, and then those ones will come out because the square root of a square is a number. So this is the first pair. 2 times 2 is 4, or 2 square. The square root of 2 square or 4 is what? 2. So these two break out as 2. Okay? This 2, oh wait, it's by itself. It's going nowhere. It remains in the radicand. Oh, look at this. We have two threes, two factors that repeat. A factor that repeats. Okay, so that's 3 times 3, or 3 square, or 9. If you take the square root of 3 times 3, or 3 square, or 9, the square root is 3. Remember, it always breaks out as just 1. This 3 is by itself, so it stays behind. Now look at the variables. Decompose x and x is a pair of identical factors, so these two break out also as x. And then this x is by itself, this has a power of 1, which is not 2, that stays behind. Okay, so we are ready to write down what the simplified form is in its expanded state. We're going to have the numbers that broke out, 2, 3, and x. You write the product, 2 times 3 times x. Okay, roots, the numbers that did not have enough power to break out, because their powers were 1, 2 times 3 times x. 2 times 3 times x. Okay, so this is the expanded form of our final answer. Let's go ahead and multiply it out. Our final answer will be 2 times 3 times x is 6x. Root 2 times 3 is 6x. And this, ladies and gentlemen, is the simplified form of 216 of the square root of 216x to the third power. Okay, so that's that. Alright, so how well did you master the contents of the presentation we just went over? To demonstrate mastery, we would like you to try out these problems. So try these problems out. So what you do is you, when you're done writing down the problems, you pause the video and solve the problems. And when you're done, you click back on play. And then you will see what the correct answers are. Okay, so instructions are to simplify the following radical expressions, the same instructions as the notes. Alright, for question 1, what if we have you to find the square root of 100? Question 2, square root of 48. Question 3, what if you to find the square root of 48k to the third power? Number 4, what if you to find the square root of 45b squared? Number 5, what if you're to find the square root of 200p squared? Number 6, what if you're to find the square root of 147b? Okay, so go ahead and pause this video at this time. I'd like you to simplify the following radicals. When you're done, click back on the play button to see what the answers are. Alright, hopefully you had a chance to work on the problems. The answers to the try these problems are number 1 is 10, Number 2 is 4 root 3. Number 3 is 4k root 3k. Number 4 is 3b root 5. Number 5 is 10p root 2. And then the last one, number 6, is 7 root 3b. Okay? Thanks so much for taking the time to watch this presentation. Really appreciate it. Let us know what you think. If you found the contents of this tutorial helpful in your studies of radical expressions, do give us a thumbs up. Your positive feedback is very valuable to us. If you have any questions or comments about what we covered, or if you have a request for any algebra tutorial that you'd like us to make, just post it in the comment section below and we'll be more than glad to assist. Do not forget to subscribe to our channel for updates to other tutorials such as this. More tools and support resources can be found at math.serve.com. Do check it out. Thanks again for watching and have a wonderful day. Goodbye.